Hello and welcome to the 16th lecture of our course on photonic devices. On today's lecture we're going to discuss the gain coefficient for semiconductor optoelectronic devices. So basically on our previous lecture we have derived the expressions for the rate of stimulated emission and absorption, which give us the number of emitted or absorbed photons per unit time, per unit volume of semiconductor, per unit frequency. So for instance, the rate of stimulated emission as a function of frequency was given by this expression, which is the photon flux density multiplied by this constant right here, so lambda squared divided by 8 pi times tau r. Okay, and here we have the joint density of states as a function of frequency multiplied by the probability of transitions that lead to emission, which is also a function of frequency. We argued that the rate of stimulated emission, which is again the number of photons per unit time, per unit volume, and per unit frequency, would be a product of all of these things. Now, if you substitute the ST here, the sub ST for A, you have the rate of stimulated absorption, right? And the main difference in the expression is that the probability of transitions that lead to absorption is going to be used instead of the probability of transitions that lead to emission. So F of FA instead of FE. Okay, but in a given device, you'll have stimulated emission happening at the same time that stimulated absorption will happen, right? Because you'll have some electrons in the valence band, which can absorb photons and thus gain energy and transition up towards the conduction band and vice versa. So these things will be happening at the same time in any given material. But both these processes, so in our previous lecture we talked about spontaneous emission, but both stimulated emission and stimulated absorption are stimulated processes, which means that the stimulus is incident photons that are flowing through the material. And the photons that are emitted by stimulated emission, for example, can be reabsorbed by the material itself. So therefore the medium is only going to have net gain, okay, so net gain when the number of stimulated emissions is greater than the number of absorptions, because otherwise on average all of the photons which are emitted per unit time will be absorbed by the material. So only when the rate of stimulated emission in a given material is greater than the rate of absorption will there be a surplus of emitted photon and a net gain in terms of stimulated emission. So if this condition is not satisfied, the material absorbs more light than it emits, or at least the same amount of light that it emits, and the result is net attenuation, or in the case in which the material absorbs as much as it emits, it is as if the material were transparent. But you can have either attenuation or transparency, which is not gain. If, on the other hand, the rate of stimulated emission is greater than the rate of stimulated absorption, for each photon that arrives at the material, it will generate more photons than it is absorbing, so it will be able to amplify, it will be able to present gain in terms of the impinging beam of light. So in this case the number of photons with energy HF at the output will be greater than the number of photons arriving at the material, and the material will present gain and will be able to be used to amplify light. So this is the principle behind the gain in semiconductor lasers. Basically you need to have a greater rate of stimulated emission than you have that of stimulated absorption. In order to derive the expression for the gain coefficient, let's consider a beam of light of intensity I, impinging on a small volume of semiconductor which has a cross-sectional area S and a differential length dz. Okay, so intensity is, here we're talking about intensity per unit frequency, but in general intensity I is power per unit area. So if you divide the total power of a beam that crosses a given cross-section by that cross-sectional area, you have intensity. So it's power over cross-sectional area. That's the definition of intensity with respect to light. So the beam axis is perpendicular to the cross-sectional area S, right? Light is propagating along the positive z direction. So we have something like this. We have a beam of light, okay, which will represent like this, and it's propagating in this direction. And then we have a material. We could choose any shape. Let us choose for example, a cylindrical material with the same cross-sectional area as the beam. And then what we are saying here is that the beam is propagating in the z direction, and we are taking a differential element of length dz, okay, dz, along the z direction. So here you could perhaps have z equal to 0, and at the end, at the other side of this differential element, inside the material of length dz, therefore you would have z equal to 0 plus dz, which is dz. Does this make sense? So, and we will sort of calculate the net intensity that is emitted in this small volume with length equal to dz. Now, if there is either gain or attenuation, the intensity of the beam is a function of position z, right? So because if the material either absorbs or it generates more light, the light that's coming out of the small element with length dz will be either of a smaller intensity or a larger intensity than the light that's arriving, because light will be either absorbed or more light will be generated inside that small volume. And we can write the intensity as a product of the flux density, which is, as we saw, is the product of the photon flux density, which is the number of photons flowing through a cross-sectional area S per unit area per unit time. Okay, so this will give us the number of photons per unit time per unit area. Okay, which the intensity is also power per unit area. So since this gives us the number of photons per unit time per unit area, if we multiply it by the energy of a photon, it makes sense that this is the expression for the intensity, because this will turn out to be the power per unit time, the power per unit area. Okay, so this is a way to write intensity, just the product of the photon flux density multiplied by the energy of a photon hf. And hence, intensity is the power associated with the beam per unit area along the cross-section of the beam, as we've mentioned. And I of f and z, in other words, the intensity as a function of frequency and z, is equal to the number of photons of frequency f in the beam crossing the cross-sectional area S per unit area times the energy of each photon. So it's the product of the photon flux density and the energy of a single photon, as we've just seen in the previous expression. Now, the power associated with stimulated emission, here we're dealing with power per unit frequency, right? Because everything is per unit frequency, but the power is going to be equal to the rate of stimulated emission multiplied by the energy of each photon and multiplied by the volume, which is S dz. So what are we saying here? Inside the material, we are considering a differential element of length dz, right? Differential length dz, and the beam is a beam of light is impinging on this material, and you have some light that is coming out of the other end, either because it's generated inside of the material due to stimulated emission. Okay, so light that is emitted, which is by stimulated emission, and the stimulus is the impinging beam of light, and light that is just passing through. Now we're calculating here the power associated with light that is emitted in a stimulated manner, so emitted by stimulated emission, and we've seen that the rate of stimulated emission is the number, so the total number of photons generated by stimulated emission per unit time, per unit frequency, and per unit volume. So that's the reason why we're multiplying by the volume, which is equal to S times dz, right? If the cross-sectional area of this differential element is S, then the total volume is the base times the height, which is S times dz. So because this is normalized with respect to volume, in other words, it's a number of photons per unit time per unit volume, we're multiplying it by the volume of the element in order to get the total number of photons emitted per unit time. And then if this will give us the total number of photons emitted per unit time, per unit frequency goes without saying here, but the total number of photons emitted inside this volume per unit time, if we multiply it by the energy of a single photon, we'll have the number of photons times the energy of one photon will give us the total energy, and if we divide the total energy by time, we get power. Okay, so that's the way to make sense of this. So it has to make sense that if we multiply these three things here, we have the total power emitted by stimulated emission inside the differential element of length here per unit frequency. And with respect to absorption, right, the power the power absorbed can be obtained in a very similar way. So if we multiply the rate of stimulated absorption, which is the number of absorbed photons per unit volume per unit time, by the volume in order to get the total number of photons which are absorbed inside the volume, and then multiply this by the energy of a single photon, we get the power that is absorbed, because we'll have the total energy divided by time, and this is just gives us power, right, which is the rate of energy over time. So the total power absorbed in the material is this, the total power emitted by stimulated emission inside the volume is this. And if we want to calculate the net power, so the emphasis on the word net here, which means that we're interested in the power of light that is emitted but not absorbed by the material. Let's put it like that. So basically the net power emitted in the volume S dz is the power emitted minus the power absorbed. Okay, and if we subtract these two expressions, so we subtract this from this, you'll have all of these terms are in common. hf times s dz will end up with rst minus ra multiplied by hf s dz. So this is the net power, the surplus power, the power that is effectively emitted by the material and not absorbed by the material. Now, if we want intensity, as we said, intensity is power by unit area, so we need to divide this by the area of the cross section here, so divide it by S. So what I'm saying is that the intensity will be equal to the power, the net power generated divided by area, and this area here will cancel this area here, so we'll end up with this, right? The intensity of the generated or absorbed, if it's negative, but the generated beam is going to be equal to RST minus RA times HF dc. Okay, this is the intensity of the net power generated by stimulated emission inside the material. The net generated intensity is equal to I exiting the material at, you know, the right side of the differential length volume minus I entering at the input. So we can write this in a different way, so we can get a different expression for the same generated intensity, which is this. The generated intensity is the intensity that's coming out at Z equal to Z plus dZ minus the intensity going in, which is I of Z, right? So all of this discussion here is based on this depiction here. So basically the same thing, but we're calling the area, you know, of the input side where light is impinging equal to S, and the area of the output side, the right hand side in this case, is S dash, right? And if you have light coming in here and some light being emitted and absorbed in the material, we can get the light that is effectively, you know, generated and emitted. In other words, the net intensity emitted by the material by subtracting the light that's going in from the light that's coming out, right? If you have more power coming out than you have power going in, that means that the difference is the power that is generated, the net power that is effectively generated inside the material. And the same thing goes for intensity, which is power per unit area. So if you subtract the intensity that's coming in from the intensity coming out, we'll have the net intensity generated, effectively generated by the material. So in mathematical terms, this just means that we have this expression right here. The intensity generated is the intensity at the right hand side coming out of the material minus the intensity going in, because this will be the intensity that's effectively generated inside the material. So this is just a different expression for this same expression right here. And on the next part of this class, we'll use these two expressions in order to derive a differential equation for intensity, which will allow us to define the gain coefficient. Okay, so this will be based on these two expressions that we have seen last, expression number 5 and expression number 6. So we'll keep going on the next part.